And we're going to be interested in a particular subset of these, which are fixed points. So what do I mean by a fixed point? In general, what I mean by a fixed point is just that if x equals p of x is called a fixed point. Okay. Now, what does that mean in terms of our flow picture? What is that actually telling us is going on? That's saying that I have some surface and my dynamical system exits the surface, does some crazy things out in the wild, and then it comes back to exactly where it started. Okay. So if x is a fixed point of the Poincare map, its associated orbit is periodic. And more than that, we actually know the period of the orbit. The period of the orbit is exactly the return time of that point. Okay? Now, a word of caution, and this is part of the difficulty with choosing good Poincare maps, is that the converse of that's not necessarily true. So you can have periodic orbits which do not correspond to a fixed point of your Poincare map under a single iteration. Okay? What does that mean? And why would you ever expect that? Okay, so imagine I had an orbit that looked like this. So it looks like some solenoid that has an associated just connecting up point, right? So this orbit is clearly periodic. If we have some bounds over our vector field, we can even get some bounds on the period of this orbit over these entire things, right? But now imagine that I pick my Poincare section. Kind of hard for me to show here. To be coming out towards us, right? And I'm only going to have it so that it hits sort of the intersection of that binding. Okay, so it's still even an oriented Poincare section. But notice what happens. The points corresponding to this orbit are mapping here to here to here to here to here, and so on, and then it maps back. Okay. So you have to be really careful, because even if something is truly periodic in the flow, the Poincare map can sort of hide that from you by having this sort of recurrent structure, where maybe it's not a fixed point initially, but it's a fixed point of 10,000 iterates of the map. And this is part of the difficulty and the work of choosing a good Poincare section, is that if instead we were to have picked this section right here, now our map is much more boring, right? It's just mapping itself. But this fixed point is really encoding a lot of what we're doing. So it's going to sound counterintuitive, but as opposed to maybe some of the other things with chaos, boring Poincare maps really do carry a lot of great structure. Okay, so we're looking for boring maps. Okay. Now, how do we actually understand these things? Well, even this situation is really complicated. So let's say we're dealing with flow in 3 dimensions. You're still dealing with a 2-dimensional hypersurface, and now you're mapping a 2-dimensional hypersurface into itself. And so visualizing that becomes really difficult, because in order to truly visualize it, we have to map it into a 4-dimensional space. Okay? Some graph in a 4-dimensional space. Or it's really, I'm sorry, it's some level curve in a 4-dimensional space. It's a Lagrangian manifold. Anyways, so how do we fix that? Well, one of the things that you're going to see on the homework is that, let's say that we do get some sort of Poincare section, and we can sort of plot out all the points that get mapped to in that Poincare section. So you can sort of think if we do a bunch of iterates of some orbit, these are all the points that gets hit somehow, okay? And then we can say, well, if I just, instead of looking at every point individually, I see that these look on a line, and I just consider the radial distance along the curve, then you'll get a much simpler picture, which becomes a one-dimensional map to a one-dimensional map, and it'll look something like this. So you get this upward bit and then the downward bit. Right? This was very similar to what we were talking about earlier about the Baker's transformation, where you sort of fold the dough over and over again, and eventually it mixes up. Okay. And with the idea that we're looking for those fixed points, right? Because if we want to orient ourselves in the midst of all this structure, we want to look for these fixed points in the periodic orbits and stuff like that. What you can do, if this is xn, this is xn plus 1, what is a fixed point? Fixed point is xn plus 1 equals xn. Okay? And so what does that correspond to on our graph? Well, that would correspond to this line right here. And there, the intersection of these two curves is going to be a fixed point for our Poincare map. So great, so we found some fixed points, and that corresponds to some periodic orbit. All is hunky-dory, great. But we weren't just interested in the periodic orbits themselves, right? We were also interested in this transverse behavior. Okay, we're interested in how these trajectories nearby are separating. So if we want to understand the stability of that periodic orbit, is there any way that this map can sort of help us understand that? And the answer is yes, right? Now, how does it let us do that? Well, what you can imagine is that we have some fixed point near here, right? And the derivative in this one-dimensional case, so if this is the induced map, if the magnitude of this at the fixed point is less than or equal to 1, that would tell us that any trajectory, which sort of starts off nearby here, gets closer and closer and closer and closer, which is exactly the stability that we're looking for. So this is what would be considered a stable periodic orbit. If p prime of x at that fixed point is greater than 1, what does that mean? That means as you iterate this map, very small variations in this initial thing blow up. Okay. And if we want to understand a visual aid to sort of how we can think about these one-dimensional maps to sort of get some intuition, we can employ a technique known as cobwebbing. So what is cobwebbing? Well, I start off with a point down here somewhere, right? I start off with some initial point. And then I'm going to map up to the value of the function. Okay? So intuitively, what this is just saying is I'm going to take a point and map it according to the function. All right? So it goes somewhere. And then if I want to understand the next starting point, what I can do is use this and map back over, right? So by going to this line where xn plus 1 equals xn, I'm effectively setting up a new starting point. Okay? And then I do it again. I go over and I do it again. And what you can see with some of these maps is that we end up in these strange motions where maybe we approach some sort of cycle in the Poincare map, but it's not actually going towards a fixed point. So this is giving us some idea of some structure, but it's not a periodic orbit, and it's telling us that that periodic orbit is not stable, at least locally. And likewise, even if you don't reduce to this one-dimensional case, you know, this is mathematicians love starting off with this sort of stuff because it's nice and easy to visualize and you can sort of draw everything and everything's great. But even in 3 dimensions, right, what we're really interested in is are these maps along these hypersurfaces. So instead of resulting down to this case where we're looking at the derivative of a single map, you can look at the Poincare map as a map from your surface to your surface, right? And that has some induced derivative along the surface, which we could talk a little bit about how you find that, but effectively it's the exact same thing you would expect, right? If you have local coordinates for your surface, you just plug those into your point and then take the derivative with respect to those coordinates, right? Yeah, 1 second. Let me just finish this up. And then boop, the eigenvalues of this map tell you about the stability of a fixed point, which in this case, the fixed point of the Poincare map, once again, is a periodic orbit of the flow. Right. So there was a question in the chat about how you get the one-dimensional for a surface. So this is actually where we do lose a little bit of information. So there's no great way to fully encode the dynamics along the surface into 1 dimension, unless we know for a fact that there's some collapsing happening onto a single dimension. We'll see in many cases that actually is what's happening, because there's some sort of contractivity going on in our flow. But for right now, when we're looking at this trick of turning this into a one-dimensional is really just relying on the intuition that if this is our Poincare section right here, so this is our Poincare section, and these are all the points that are getting hit by our flow along this plane of some kind, right? Then really the only thing that we need to describe a point in this sort of object is the radial distance away from the origin. So it's usually like some sort of thing like this, and then it goes beyond, and then there's like a little kip up, and it goes back, and something like this, right? So we are losing a little bit of information when we go from that from the full 2-dimensional mapping into 2 dimensions into this 1-dimensional map, right? But our hope is that if you can understand this radial 1-dimensional map, then that will give you a better understanding of this 2D into 2D map and will help you search for fixed points and search for these periodic orbits, which are really going to sort of dominate the conversation in terms of the flow. Does that make sense? Angry, upset, somewhere in between? So it's just a choice, right? Can we be sure such a 1D map exists? So you can definitely be sure that the 1D map exists, right? You can just construct it explicitly. So if I have a point, I can just give you the radial distance, and that will be a map. And if there's a fixed point to my original system, it better be a fixed point to the radial system, right? So absolutely, the map will exist. Can we be sure that such a map captures everything we want out of this 2D to 2D mapping? Absolutely not, right? Absolutely not, we cannot, right? That is something that's all about using extra information about the system. So if you have some system which really doesn't collapse at all onto these lower dimensional spaces and just sort of keeps going and explodes out and like maintains this like much larger structure, then we can observe different one-dimensional images of that thing, right? But those 1D maps are not necessarily telling us the full story. That's just a consequence of the fact that, you know, we're trying to understand many dimensional objects by smaller dimensional things that we can work with.